All right, guys. So the question was how we're going to evaluate lab M and N. Since we don't have a lab test for these two labs and they are sort of kind of a long lab, I'll ask your TAs to evaluate it based on the correctness of the results and also the approach you've chosen. It doesn't have to be completely correct to get the full four point, but I asked them just to be completely uniform, see all the solutions first, and then decide how to grade. If you have made a mistake a little bit, like one or two here and there, that shouldn't affect the final grade, but they're gonna evaluate on the overall performance. And also we have the similarity checks for the submissions, as I mentioned. So you're gonna be given minus points if we found there are similarities between your codes and your colleagues. So again, make sure for lab N, do that individually, right? Treat them as your lab test. You can discuss things and approaches on how to, tackle the question and how to solve it, but you have to write it yourself. And as you know, it's programming languages, so there are like unlimited ways to write one algorithm. So chances are very low your code should be the same. Of course, there are some boilerplate codes here and there because your wiring would be the same and so on, but that would only be like 10%, 15%, right? The rest should be different. Yeah, this is the way we approach grading lab M and lab N. All right.
Okay, thank you.
Yeah. All right. Any other questions? You have more than a week. I mean, we are actually more lenient. Otherwise, uh, every single mistake would have cost you points. And I exactly mentioned it now that I asked them just to evaluate it on overall performance. Also, you had more than a week for lab N also and also for lab M, so that should be fine. No worries. And the lab grades were already high, so lab A up to lab um, L, they were mostly very high. So I guess the overall grade for this course is way higher than the average. So that should be fine.
I have another question.
Yeah.
Is chapter 5 more fun than chapter 4?
So it depends how fun was chapter 4.
4 wasn't fun.
I guess 5 is good. Yeah.
Is it a build up from 4 or is it going to be something a bit different?
I mean, I like both of them. I like pipelining because I really liked it when I was studying it as a student. So I'm sort of biased on that. But some people like um, assembly language programming. Some of them like Verilog more. So I suggest them if you really love programming in Verilog, so perhaps you're a hardware guy. So you need to consider a career in computer hardware instead of software engineering. So it just depends on your preferences, right?
Yes.
Yeah.
Okay.
So let me share my screen. Okay. Can you see the share screen?
Yeah.
Okay, sounds good. Any questions before we start? Okay. So I'm saying,
Professor,
yeah, go ahead.
will this lecture will be recorded then
Right.
posted online?
Yes.
Okay.
Yeah. So I'm seeing like 20 some people are in. So let me just wrap up what I said like some minutes ago about the the final. So I'll post some sample questions and answers from chapter 4 tonight. Also, either tonight or next week, Monday, on the first hour, we're gonna finish chapter 5, which is memory hierarchy and cache. And just like your midterm, I'm gonna plan to have a review on your final exam. Okay. We haven't decided the method we're gonna have your final exam online, but nevertheless, it's gonna be online. I'm trying to resist not to have it multiple choice question, but we are trying to explore other possibilities. Okay, it will be on the same day as before, as was announced by the department. So there are no changes on the date of the exam, but the only change would be that it's going to be online. So nothing really changes for us. If we manage to make it non-multiple choice, a written exam online, that would be the best option, the closest one to what I had envisioned when I started, this course. Otherwise, we're gonna go with the multiple choice questions and using Moodle. So either of the two ways. And since you've already polled to reduce the weight distribution, so that shouldn't affect that much of your final grade. Okay. But I hope the outcome would be good. I'm seeing that the average grade of the class is so far is very high, so that's fine. Okay, any other questions? Just another point that course evaluations opened as of today. Make sure to spend some time. It won't take you more than 5-7 minutes to complete that. It's going to be very important for us to see your feedback, especially for me, to hear your feedback. If anything was good, please mention it. If anything could have been better, also do mention that as well. I appreciate your feedback. Okay. All right. If there are no questions, I'm going to start chapter 5 in a minute, I'll say. Yep.
Prof, I have a question.
Sure.
It's regarding the like course withdrawal and drop date. We received an email that said that the date to drop a course has been extended. Do you have any information regarding that?
No, I'm afraid I'm not a good resource on that. Perhaps you need to check with the undergrad office, right?
Okay, sure. Yeah, I was just wondering. Thank you.
Yeah.
Well, I'm good for this course, by the way. That was just for other courses.
I see. Okay. Let me see how many of you have already submitted your course evaluation. Not many. So please do spend some time to write down the course evaluation, okay? I really appreciate it. If you felt like, as well as course evaluation, you needed another place to submit reviews, I mean, you know better than me that Rate My Prof would be another place. But for internal evaluations of the department, we normally use course the official your course evaluation. Okay. All right, guys. I got you. Great. So let's get started then. So feel free to unmute your microphone if you had questions, because I might miss the chat when I'm looking at the slides. So feel free to disrupt me, unmute your microphone, and then talk about anything that wasn't clear enough for you, so I can go back and answer questions. All right. So last week we finished chapter 4 with the pipelining. Next week we're gonna review that example again, and I'll post some sample questions on chapter 4 as well, so you're going to have more clear way to how to approach that. But the exam question would be pretty close to what we went through last week. I didn't like the way your book was approaching pipelining. So for pipelining, just stick to that example that I provided last week. All right. Chapter 5 talks about memory hierarchy, and which is namely cache, right? You might have heard the word cache, the buzzword. We're going to go into details about what are the different models of memory hierarchy, what is actually a memory hierarchy, and how we're going to compute the latency of using a memory hierarchy. What are the advantages? What are the pros and cons of having a cache in your architecture, right? Okay, so let's just go back to the old figure, that the classic figure we started the course with, for which you can think about the your computer, right? The processing system of a computer as something that inputs data through, you input data through, and there are something that are, let me just try it this way. Okay. Okay, so you can input data here, and then there is a control module. You saw so many things about it on chapter 4. How we're gonna, those control bits could control your pipeline, and then you have a data path which the data flows into. So input, you're gonna have a control unit, and then you're gonna do a so inside your processor, this is where the actual processing and computations happen, right? But however, every time you need to have a processing element done, right, you need to access your memory, right? And depending on the way we define this memory, the architecture of the memory, you're going to have different way to utilize these data that are coming, right, in order to load and also access and also store later, right? So you're going to store back. So in this chapter, we're going to expand this and to see what are the hierarchy of the memory. Like think about it as a cone, right? As a hierarchy. So you're going to see that later on, that the closer you are with your processor, so which is this, so I'm just going to call this CPU, the closer you are in the CPU, because this is closer, your memory would be smaller, thus your access is faster, right? The further you get, right, think about it this way, the further you get from the actual CPU, you are willing to have a larger and larger and larger memory. However, because it's further away from your CPU, the access would be taking longer time, right? And that's actually a trade-off that define your memory hierarchy. Are we willing to have more size and a slower access, or are we going to have a smaller size, right, but a faster access? So the trade-off between these two objectives will define how we're going to define an architecture of memory, all right? And we're going to talk about it in this chapter.
I have a question.
Sure.
So for the memory that you're talking about, is it related to the one we have in our own computers, which is like an 8 GB RAM or like a 16 GB? Is this the one you're talking about?
Yes, exactly. So the memory we are talking about, one of the elements, I'm just trying to just figure out this digital pen. This is better now. So RAM is one type of your memory, right, which is pretty larger than your cache. Okay, if you recall, in your memory, in your CPU, right, in your processing unit, when you buy, for instance, an Intel i7, Intel i9, it's going to tell you L1 cache has this amount of kilobytes of size, and then you have L2 and L3 which normally gets bigger and bigger, right? So whatever element that are writable to and that can be accessed, we're going to call it memory, right? So RAM would be one element of the memory. We can also call a hard drive, a hard disk, also another memory, which is pretty much very, very, very bigger, larger, but it's going to be slower. So we're going to talk about them in a few slides, okay? Now, let's just go through a simple example, and you're going to understand why actually we need a faster memory hierarchy. Why it's not only one single element of memory, such as hard drive or RAM. For instance, there is a principle of locality, right, which comprises of two different locality. One, it is called temporal, okay, temporal locality, and the other one is a spatial locality, okay. So basically, for every code segment that you are running, especially those that are in loops, you can define what are those temporal and spatial localities, right? Some variable might be placed in both of them, but the principle of locality basically defines that sometimes you need to access some elements in your code much more than the others, right? Either in temporal mode at times, right, or at iterations, or in a spatial mode, which is if you have an element, you might access the elements nearby, right, in their distance. That's why we're going to call it the spatial locality. Or there's another term for that spatial locality we use as contiguous. You might have heard the contiguous elements, or you will be hearing it much more in parallel computing courses, parallel programming courses, because the contiguity or being contiguous next to each other is a very, very important factor when you are running a large segment of code inside multiple loops, right? Assume your loop is running 1,000 times, 1,000,000 times, and you're accessing elements inside an array, right? So how close they are, how in order you're accessing will determine the final performance of your execution. And at some point, by just changing a little bit of your code, how we're going to access those and play around with the spatial or temporal locality, you're going to have a huge speed up, okay? Let's have an example with a small code segment, right? Okay, so we're going to have two nested for loops, right? And we're going to iterate over I. Sometimes we call this I induction variable. So your I is from 0, and as long as it's smaller than 20, you're going to increment I by 1, and then your J starts from 0, and as long as J is smaller than 10, you're going to increment J by 1. Then your computation would be something like you have an array of A. At each of the ith element, you're going to update the value of element I of A by a multiplication of AI and J, right? And then you're going to update A of I. All right. So right out of the, can anyone tell me what are the temporal and spatial variables are here? Any suggestion?
I should be spatial and J should be temporal.
So why I should be spatial?
Since we need to wait a long time to get I change, so I can be like we don't need to get it as soon as we want, but we need the J very quickly.
Okay, so I would say partially correct. So your temporal was correct. Temporal is when you have to access in different iterations, right? Or at different times. Yeah, so your friend is writing in the chat, shouldn't it be A of I for a spatial? Yeah, you're correct actually. So Let's see why. So you see at every iteration, now we are playing around with I. At iteration 1, right? I'm just gonna call okay, iteration 1, your I would be 0, right? And then it's gonna be 1, and then it's gonna be up to 20, right? But at iteration 1, your J also would be 0. Well, actually, this final iteration would be 10 multiplied 20, right? So that would be I multiply J times. Your J would be 0, right? And for every 10 J, 1 I will increase, right? So this would be like J up to 10, and then 1 would be again J from 0 to 10, and so on and so forth, right? So 0 to 10. This is 4. Okay, so you simply can see that temporal variables, definitely A, I, and J are one of those temporal variables because they are changing at every iteration, right? Also, the other thing that is changing is the value of A of I, right? The array of A of I, because at each iteration, at each temporal iteration, we're gonna update the value of A of I, right? So it's an array A, right? This is 0 element, and this is the last one. This is ith element, right? So depending on so this is the array A, right? So at each of those iteration, we are updating one of these elements of A. However, for a spatial means those that are contiguous, right? So think about this array as a chunk of memory, right? You're writing to. So at some point, at each of the iterations, when you're updating I, you want to access I minus 1 or I plus 1, right? Okay? So that's why if you're categorizing these two, we can say that I, J, and A of I could be a temporal, right? They're using the temporal locality. And for a spatial, we are using that for A of I because there's contiguity involved here, right? At each of those iterations, we are accessing the contiguous locations, memory locations of array, right? So your colleague was correct.
I have a question.
Sure.
So what's if I have an array? What's the main difference between a temporal and spatial?
So let me just for depending on the way you are looking at this, spatial locality is the items contiguous to each other, right? For instance, A of I minus 1, A of I, A of I plus 1 or plus 2, right? Those are accessed recently. So at each iteration, you might access them again and again and again. So depending on the algorithm, which are many instances, for instance, in scientific computing, many of the cases are spatial locality because for instance, in matrix multiplication, you're accessing multiple contiguous locations inside each matrix, right? You wanna multiply a row with a column, right? So the elements of the rows and the element of the columns are going to get accessed more recently because you're trying to multiply and then you're going to add the results to compute the final multiplication, right? So those are using a spatial locality, right? For temporal locality, the definition says just the items accessed recently are likely to be accessed again soon, right? For instance, as you saw in the example that I provided, I and J, right, which are induction variables. And by induction variables, we are talking about those variables are getting incremented or decremented, right? So those are part of a temporal locality principle. In this example that I provided, we had both cases. I and j and a of I were referenced, right, recently more often. And for the spatial one, we were accessing the contiguous element of a of I, okay? Because a has multiple elements inside, and then the contiguous elements are getting access. So these two principles are determining how we're gonna define a memory hierarchy in a system depending on the application we're targeting, okay? So that actually lays the ground for us on how we're going to define the architecture, right? We are trying to take advantage of the locality to define such a memory that we can use this in a most efficient way, okay? So, for instance, if we are trying to adapt a system that takes advantage of the locality, both spatial and temporal, right? So we need to find a way to store things on disk, right? For those things that are less frequently accessed, and copy recently accessed, like make them nearby. Just like when you're working at home, let me just see, there's something on the chat. Yes, A of I is both temporal, yeah, and spatial, right? So assume you're studying for your exam, right? You might have some draft papers right next to you because you are trying to just calculate something on paper and you want to access it all the time. You want to make sure that this draft paper, right, is as close as possible to you because you are using it all the time. However, perhaps one of the reference books that you just saw it 2 months ago and you don't want to have a look at it for another 5 hours, you might just put it in the next desk because your desk is now full of other draft papers, right? So you are determining that, okay, for those items that I'm accessing more often or that are likely to get access more often in the near future, let me just have them close to me because I'm going to access them more often, right? For those bulky stuff or some items that I might not access or I might not need to access, right, in a short amount of time, I might just afford it to just put it over there. If need be, I'm just going to stand up and then walk over there and then fetch them, okay? So this is exactly what's happening in an architecture of a memory. So those items that are going to get accessed recently or will be accessed recently, you want to put them closer to you. In the paradigm of a computer, instead of a disk, you want to put it in your RAM, right? In your main memory, which is closer to your processor, all right? However, in memory hierarchy, we have another level of hierarchy, which is even closer than RAM to your CPU. And we're going to call it cache, okay? Cache memory. So those elements of cache memory are even smaller, right, in size with respect to your RAM and with respect to your hard drive. But at the same time, they are way, way faster, okay? So you might want to put something that you want to access pretty often and you want to access it fast, okay? For instance, you're computing inside a loop and you want to save the partial result of a matrix multiplication before addition, right? Those partial results, you know that you're going to use them. So if you find a way to access those in your cache, you can speed up your computations by a large factor. With respect to just save them back to memory or even put them into hard drive as a file, and every time you just go and fetch and search all those gigabytes of disk, right, to find that specific 4 kilobytes of data you were interested in, okay? So that's actually how we can take advantage of locality of memory or memory locality, okay? Let's have a look at another figure. So,
Question.
Sure.
So does the individual cache has a limited storage, or can it store anything else?
Yes, and that's exactly the dilemma of how we're gonna define it as computer architects. Okay, how we're gonna define that? How we're gonna use that? Because it's gonna play a huge difference for us. So in this figure, you're gonna see that your processor is on the top of that hierarchy, right? So the closer we are, the faster it gets, because your bus, which is a lane that the data goes through back and forth, is going to be shorter, so your latency would be shorter. And also the technology used in cache memory or RAM or disk are different. That also plays a huge difference, a huge factor in how we're going to fetch data, okay? So, let's see here. Yes, almost. That's right. But this is more in hardware. Yeah. Okay. All right. So now the question is, what data are we going to put in the closer, smaller memory, which we call it cache, and what are the rest that could be put in the larger, bulkier, and slower memory, which we can call it a RAM, or even larger than that and slower than that, which is a hard drive. Okay. All right. There is a notion, there's a definition that when we want to access something in memory hierarchy, it always goes down the hierarchy this way. Okay. So what it means is we start from the processor. Definitely first, we're going to look into the closer location, the closest location, which is cache. Okay, your cache might have different levels itself. In modern CPUs, you have L1, you have L2, you have L3, like level 1, level 2, and level 3 cache. L1 should be the smallest one normally. In Intel i7, when you buy a CPU, it normally is written like, I don't know, 32 kilobytes of L1, and then some hundreds of kilobytes of L2, and then might be some megabytes of L3, right? So inside the cache, you also have a small memory hierarchy, right? For which L1 is a smaller one. So if a processor, if a program needs to access something, it's going to first look at L1. Oh, am I going to find it in L1? If it's there, awesome. We're going to call it a hit. So you found your data, you're going to retrieve it back to your processor, okay? If you don't find it in your L1, we're going to call this a miss. We were looking for something, a block of data, we didn't find it, so we miss it. Now the process goes down the hierarchy. If it was L1, we're going to go to L2. If it was L2, we're going to go to L3. If it was L3, we're going to go to RAM, right? And if it wasn't even in RAM, perhaps we need to go to the hard drive, right? HDD. Think about it as RAM. In this, in most of the examples we have, we might just ignore L3 for simplicity, but this is the same concept, right? So you have some cache, some levels of cache, you have RAM, and you have hard drive, okay? Let me see what's happening in the chat. So, yes, and we want to make sure we put aside some of those data that are going to get accessed more often, or they are likely to get access because you're accessing their contiguous memory, right, next to each other and close to us. For instance, that array of A, right? If you think, oh, I'm going to use them all one by one, plus one, A of I of plus one. So an intelligent programmer, when he tries to rewrite the code in a parallel programming, he might just say, why not I cache those elements block by block instead of element by element. So if I miss one, I don't miss them all the time, right? At least I have 8 of the elements at the same time, so I can reduce the miss ratio by a large margin, okay? What if we don't find it all on the levels? So you just have to come down to the hierarchy, right? You start from L1 and then you go to L2, L3, RAM, and then your disk, right? Finally, somewhere down the drain. I mean, we can just ignore hard drive for now. We can just talk about RAM versus cache. So finally, we're going to find it somewhere in RAM, right? But we are paying a price of missing all those specific accesses, right? Because for each access, if we don't get it, You miss it. And by each miss, you're paying a huge price as a penalty, what we call it as a penalty, because you were looking for something and you couldn't find it. Now you have to go back one level inside and look for that. And that level inside is lower than the first level. So that's a penalty you're paying added to the search in the to the secondary level, right? Or the third layer. So that's why if you miss, you've already missed, and also you have to pay a penalty to find the data in a lower level. Okay.
Prof, does the RAM have levels as well?
Not that I've known of, no. I mean, you might find an architecture with some levels, but in a normal computer, no, they don't have.
So like the time to access a given information from the RAM is going to be equal, like?
Again, so depending on the architecture of the RAM. So when your RAM, that's why your RAM is external from your CPU, okay? Your cache is normally part of the module of the CPU when you buy. When you buy an Intel CPU, the cache was embedded inside because that should be closer, right? But however, you remember when you want to buy a RAM, the frequency of the RAM must match the frequency of your architecture of your CPU, otherwise they won't work. And each RAM, depending on its internal speed, it might able to find on average certain blocks in some microseconds, milliseconds, or nanoseconds. We're going to see some results in a few slides, so you have a better idea.
Can you give an example of when you say the architecture, like it has to match, like what's under what label is it? Like,
sure.
Like, you know how you give an example for the cache, you were like it's L something. So like what would that mean?
Sure. Now, if you look at this table that I'm providing here, so this magnetic disk is normally used on your hard drives, right? Now we have flash hard drives, but just think about it as the older generation of hard drive, which it had actually a disk. When you power on your computer, you could have heard something rotating, right? There are disks that are rotating, and it's a magnetic disk. So you see the typical, by typical, it's an average over many, perhaps thousands or millions of accesses. So on average, you're going to see that, okay, on average, a typical access time for a hard drive, it might be within 5 million to 20 million nanoseconds, right? And nano was already 10 to the raise of -9, right? However, the price, I mean, these data are from 2012, like 7-8 years ago. It's going to be per gigabyte. It's pretty cheap. We can buy like hard drives. Nowadays, you can buy hard drives of many terabytes, right? With less than $200. You see, it's a bulk of data, but it's much slower than what you can get from a flash-based hard drive, which is this, or a flash or a disk drive, right? But at the same time, those are smaller in size and they're expensive. So the more you go up into this ladder, you're gonna see that this is your RAM and this is your cache, right? SRAM, we call it. So you see the typical access time is very smaller than you're gonna find in your hard drive. It's a fraction of million, right? On average, it was 5 million nanoseconds. Now this is around 1 nanosecond, like in a factor of 5 million times faster from a hard drive, in a factor of 5,000 times faster than a flash drive, and a factor of 50 times or more faster than your RAM, right? So if you are an intelligent software programmer that and you want to make sure that the code that is given to you is going to perform as fast as possible, you need to find a way to set aside those elements of your application that are going to get used more, or at a certain iteration or at a certain order, put it one after another inside your cache, right? In a way that you have the least amount of cache misses and the highest amount of cache hits, okay? Because every time you miss something, You have to find a way, go down in memory, and then fetch it, and then bring it back up into cache, and then access it from the cache. There's no direct way to access memory. Whatever we access should go down the path of memory hierarchy, okay? Okay, let me answer some questions in chat. So once there's a hit, it copies the block of data up to the smaller cache for the next time. That's correct. So once there's a hit, well, actually no, once there's a hit, you already found it, right? You were looking in the data, you were looking for an address of a data, you found it in L1 cache. So that's a hit, you just fetch it right away, okay? If you didn't hit, for which you look for data, you couldn't find it in L1, now you have to go to L2, right? So the price you pay is, first, you missed your L1, and now you have to go one level lower, which is a little bit slower, and then you find it from there, and then you bring it back up to L1, and you access L1, okay? So this is called a penalty that you're paying. So you have one miss plus a penalty to find it from L2 and bring it to L1, okay? Remember, all the time we are accessing data from the closest memory to the CPU, which is L1. You just have to find it somewhere down the hierarchy and then bring it back up, okay? That's why if you go further into the deeper hierarchy, the penalty would be higher because you have to keep bringing it up and up and up, right? Cookies are not related to cache, but they have the same sort of notion in software domain, not in hardware. So they thought one usage of cookie in browsers would be to add some information about the way you browse, and also cookies has other purposes. It might be just for verification and security purposes, right? So these have a little bit of different notions, but yeah, at some point you can have some relative, similarities between those as well. All right. So the DRAM technology, okay, your RAM. Normally, we can define. Let's put this here. Okay. So this is a figure of a modern DRAM, right? As you see, they're organized in banks, right? We call them banks DRAMs. Let's see if I can. Right? For DDR3, which was back in 2012, now we have DDR4 and perhaps 5 is coming soon, right? We had 4 normally banks for DDR3. And each bank was consisted of a series of rows, right? Each of the rows could be accessed independently by sending a pre-charge, right? Which was communicating with the rows inside a bank, and a row address was sent with an acknowledgement or an activate. So this is a pre-charge, and this is an activate. Which causes the row to transfer into a buffer, right? That would be a buffer inside your RAM. And that buffer would send it back, that row, okay, towards the processor to read it back, or towards the higher level, which is the lowest level of cache, right? If you had only 2 levels of cache or 1 level of cache, it will send it to 1 level higher, right? So when the row is in the buffer, it can be transferred by a successive column address, right? And a column address is normally with a range of 4, 8, and 16, okay? And a block was sent up to the next level, okay? So basically this figure is trying to say in high level that your RAM, right, consists of banks of data, right? If you open the black box of a RAM, DDR3, like in 2012, if you search now, we have DDR4 and 5 in for i9 or i7, there are 4, and perhaps 5 is coming soon. I'm not sure, but yeah, just you can Google it and see when DDR5 is coming. Perhaps it's out already. So your RAM consists of banks of memory, and each of those banks has rows, right? When you want to fetch some data from your RAM, you need to send a pre-charge signal, and then it's kind of return and activate, which consists of a row of data towards a buffer, and then you're going to send this buffer back up to the last level of cache, okay? Or if you didn't have any cache, it's going to send it directly to your processor, okay? This is how we process that. Normally, it's either in a row base here, okay, or a block base. It's not individual data. So by which level of cache would it send to? The lowest level, right? If you had only L1 and L2, it would have sent to L2 here. If you had only L1, it would have sent to L1. If you didn't have any cache, it would have sent directly to your processor, okay? All right. So these are some information about the way we started with the capacity of the DRAM generations for our RAM. So this starts at 80s. I mean, this figure could have started much earlier because we had computers before that, right? And then you see this data that starts from 80s and up to 2007. You see that the capacity was way shorter, but the cost was way higher for 1 gigabyte. I mean, there was no 1 gigabyte memory unless you just add multiple hundreds of 64 kilobytes together, which would cost you a lot of money back in 1980s. If you recall, like the early computers didn't have much of some kilobytes of RAM, okay? But nowadays we are in the order of tens of gigabytes of RAM, like 64 gigabyte, 128 gigabyte, or 32 gigabytes. So when you buy a very random laptop, it wouldn't have anything lower than 16 gigabytes of RAM now, right? And then you have this TRAC, okay, which is the time required to read any random single memory, okay? That's why we call it a random access, or RAM, because inside that block that I showed you in the previous slide, on average, it should provide a random access time for a given bank and row, okay? And that's why we call it RAM. It's a random access memory, because in either of those locations of the bank, it should be able to guarantee at some point some range of access time, okay? The other one that you can see here, because this figure shows TRAC and TCAC, so that TCAC is the column or page access time. So it's the time required to get data at the output, okay? Which is gonna be a little bit larger than this, because this will involve adding the buffer time and send it back to the upper memory, right? That's why it's gonna be a little bit higher. SRAM is actually what we call it cache, okay? DRAM is the classic RAM, you can think about it, okay? Yeah, now most of the systems has two, because when you buy a CPU either from Intel or from other company, normally they have cache embedded inside the same chip of your processor, right? If you buy i5, i3, i9, i7, it has cache inside. When you Google, you can see that each architecture of the CPU of Intel, for instance, has its own predefined L1, L2, and L3, right? But for RAM, you can buy it individually. But the only thing that you should consider is when you buy a RAM, the speed of the RAM should match the speed of your processor, right? if your processor supports DDR4 or DDR3, your RAM must be DDR3 or DDR4. You can't mismatch these two, otherwise they won't work, right? Because the same frequency should match these two, all right? Okay, this is just more information for you, this table. You see that just like that figure that you saw by the advancement of the technology, right? Not only the size advanced and got bigger and bigger, your price was getting lower and lower per gigabyte, right? And total access time is going to decrease because your technology got better, right? If you recall Moore's law, so we are approaching more and more towards Moore's law because you make the systems smaller and smaller, so the access time went and decreased. At the same time, your speed increases. So at the same time that your size increases, you can also reduce the speed. Okay, the access time decreases, which is getting faster. All right. So some factors for your DRAM performance: row buffer, because you are accessing it per buffer, per row, and then you want to load it into a buffer. So the architecture of the buffer determines how fast your RAM would work. Okay, if it's asynchronous or it's not, so it's gonna plays a huge role. And also the way the banking has been designed, right? If it's in 1 dimension or 2 dimension, now we are thinking about some companies are thinking about the 3D RAM, which is going to be a revolution for RAMs. So that would play a huge factor for this as well. Okay, these slides are more or less some background slides, so you don't have to memorize this. Okay, you just have to learn them and get the concept from. Okay, now we go to the flash storage. What I've seen it in many different application of flash storage. You have micro SDs, you have SDs, or you want to have small USB keys, right? So these have a non-volatile semiconductors. Okay, they are faster than disk. Okay, smaller, they require lower power, but they are more expensive. If you want to have a very large size of this, you know, in the order of hundreds of gigabytes, it would be more expensive than your RAM or your disk. Okay, these are the type of cache. These are the type of flashes. I mean, again, you don't have to memorize them. You have two major classes, and normally, as you have noticed on your, for instance, USB keys, after many thousands of read and writes, and mostly writes, their bits are wearing out, and out of a sudden you might just lose your data on your USB key. Okay, I'm just gonna go fast on this. So this is your classical magnet-based hard drives, right? That was the disk actually, right? That was a disk that was rotating. Okay, and that was just like your old gramophone, right? It was trying to access data when it was rotating. Okay, so you have cylinders and you have some sectors, and each of those sectors has some tracks. Okay, and these would point into each of the track and just grab data. Okay, while the magnetic storage was rotating. Okay, just like a gramophone. And that's why it was advised that not to shake your hard drive or your old computer or your laptops, right? Because it's going to mess up with the way you're going to access this, and it might just disrupt or even corrupt your hard drive. Okay. I'm going to go fast on this as well, but just to give you an example for a disk access example. So assume you have 512 sector. Okay. So this is called a sector. Okay, just a small chunk inside each of the tracks within your cylinder. Okay, you have 512 of those. Where are we? Yeah, 512. So the speed that this magnet disk is rotating is 15,000 rate per minute, right? For each minute, it's gonna rotate 15,000 times, okay? And the average seek time, it has been benchmarked that it's gonna take 4 milliseconds, okay? And when you seek and find the specific chunk, the transfer rate is 100 megabit per second. So at each second, you can transfer it 100 megabit of data, okay? There is a controller involved that controls the overall process. It has its own add-on delay or overhead. So the average read time, you need to add them all together. So you're gonna have 4 millisecond seek time. Why? Because you had 0.2 millisecond control delay already added here, okay? This is your rotational latency. It's gonna rotate 15,000 times per second. I'm sorry, per minute, because it's rate per minute. If you want to convert it to a minute, right? To a second, you need to divide it by 60 because each minute has 60 seconds, right? And then you're gonna have a 512 divided by 100 megabit, because each of those sectors are gonna get transferred with the 100 megabit per second. All right. So you add them all three together, you're gonna have to have something around 6 milliseconds of read time on average, right? So if actual average seek time is about 1 millisecond, the average read time would have been 3.2 millisecond instead, okay? Now, let's go to, yeah. So these are the issue with the disk, which is normally, you know, we have different type of disk now. We have SCSI, we have ATA, we have SATA. Now we have flash-based disk as well, but that's mostly out of the context of this chapter. Let's talk about more interesting stuff, which is the cache. Okay. Now we arrive to the point that we have this in this memory hierarchy. We have the processor. Think about it as your CPU. Okay. CPU, and this is your L1 and L2. Just think about it as two-level cache, okay? Cache, and this is your RAM, okay? DRAM, okay? Now we're talking about this, either of this. Let's talk about just L1 now, okay? Let's talk about how the cache is getting access and what is the relation between the size of the cache and the way we access it, okay? Let me just use. All right. So as I mentioned, your cache memory is the level of the memory hierarchy, which is the closest one to your CPU, right? L1 within your cache is going to be even the closest. All right, so assume this was the layout in your cache before a reference to XN, okay? We were trying to access XN here, okay? A program was running, and at one iteration, we were in need of accessing XN. We take a look at this cache and assume we have only one level of cache, okay? We were having a look at this cache, and we see, oh, XN is not found, right? So we had a miss. We go back down in the memory hierarchy, and for instance, we found it from memory, from the DRAM, and then we bring it back up here, okay? And then we access it here. Now, after the access or after the reference to XN, now this is the snapshot. This is the snapshot of the cache at the point of, perhaps this is I0 or T0 at time 0, and this is T1, okay? So at T1, this is the snapshot of the cache so we have these elements in the cache, and XN is now there. So assume if inside your code, now again at T2, we're gonna access Tn, we were in need to access Tn, now we're gonna hit it right away because it's already there, right? You don't have to pay a price of a miss. So how we choose to put this stuff here, this data here, is gonna play a huge factor on how we're gonna access them, right? There are three major architecture of cache that determines the layout of the data inside your cache, and we're gonna talk about it in this chapter. All right. Any questions so far?
Yeah, I have a question. So how many on the left side when t is equal to 0? How many misses do we have on each single row? We have a miss.
No. So you just have to count it as one miss because it's per reference, right? Your reference was to xn wasn't found, so it's one miss. So in how we're gonna search through those blocks of cache, we're gonna have one slide on that. So it's a hardware, and on app, just like your hard drive, which gives you an access average stick time, right? Inside your cache, the hardware that has different lanes is gonna give you an average stick time, but the price you pay for each reference is one miss, right?
Okay, and then for the example that we just did, do we need to know it for the final?
This example?
Yeah.
It's pretty straightforward. We have more interesting questions to focus. I would say no, but I mean that was like some additions, right? You have some control latency, some rotation latency, and you would just add them together, right?
Okay.
All right, let's talk about the first architecture of the cache before we have a break. Okay, let's carry on for some more minutes. So the first architecture of the cache is called direct mapped cache. So what does that mean by a direct map cache? So assume this is your cache, okay? And this is your memory, okay? You can see that your cache starts from 000, 000, and it ends at 111. So this resembles how many blocks? 8, right? Because this is in a base 2. So you're gonna have from 000 and then 001 up to 111, which is 8. Okay, that's why these are 8 blocks. Okay, and there must be always a relation between your cache size and memory size, one way or another, depending on the architecture of your cache. So if you have a cache of this size, your memory shouldn't exceed from this size, and we're gonna talk about it right now. Why? Because this block address of the cache is actually a modulo of the number of blocks in cache, okay? So if this is 8, so this must have been, right, a mod of this, which is in this case is what? If you count it here, you're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have another 10 and another 10, okay? So, and another 2 at the end. So the block address mod number of blocks in cache determines your direct map address. And we call it a direct map because there is only one choice to put your data in cache. It's directly mapped in one location. One location, so the example shows that all these grays, the blocks shown in gray, are gonna get directly mapped in this 001. Why? Because each of those, if you get a mod of this with 8, 1 and 9, both of them would return to 1, okay? Because 1 is 1, 9 mod 8 is again 1, right? You go back again, you find it here. This is also shown in light gray, and it's going to directly map to the 001. That's why we call it a direct map cache. Every 8 are going to get directly mapped to this cache. So if you are trying to find a data here, Okay, back to your question. If you're trying to find a data here, this data, depending on the size, you might have either of this, or this inside. Okay, if you're looking for something that should be end with the address of 001, it might be only representative of only this 501 or 011, 01001 or 3 zeros and 1 or 11001, because all these mods are going to go back to the 1 again. Okay, there's only one choice to be found. Okay, and that's why we call it a direct map cache. A cache is structure in which each memory location is mapped to exactly one location. All right. For instance, in this case, we had eight blocks, and so you can easily found either by getting a mod, a modulo, or just taking a look at the last 3 digits. Okay, last 3 digits of this one is 001. Okay, which is mapping again to 001, which is 1. The last 3 digits of this is also 001. That shows that it's going to be directly mapped to the block of 001. Okay, this one as well, and this one as well. And that's the beauty of using a binary language, right? Because now you can easily determine which of the blocks are going to get mapped to where. Okay. Any questions? Okay, so now this shows a very small scale direct map cache. All right, let's see how we're gonna add some more detail and make it a little bit bigger, right? Now, we understand how we're gonna map those into blocks because we can just get a mod, and then the remainder will show that what block of cache the data could be found, right? Or just having a look at those last 3 digits. All right, now we have 2 other things to add to the equation. We have tags and we have valid bits. Valid bits would be pretty easy because valid bits are always starting when you start a computer, it's going to be 0, okay, or not valid. And when you access the data for the first time, you might get a miss, and then you're going to reset the bit to valid bit, okay? And then when they are 1, they are valid. Sometimes it's a bool, right? So it's a bool. So either 0 or no, or a 1, which is a yes. Okay, so that's a valid bit. When you restart your computer, when the cache is getting flushed, so all of them are not valid, or 0 or none. And then when you accessing them gradually, they're gonna get valid. Okay. So how about tag now? So the tag, we need tag just to contain the upper portion of the address. Remember when you had that 5 digit? So those 3 were calling for the block, right? The upper 2, which could be 00 or 01, 10, 11, we're gonna call it tag, okay? Corresponding to the bits that are not used as an index, okay, into the cache. And normally we use a field in a table for memory hierarchy that contains, right, the address information required to identify whether or not the associated block corresponds to a specific word or not. Okay, so in this case, these 2 are the tags. 00, 01 is a tag, 01 is a tag, right? Or 10 or 11. It's going to just show you more information about where, in what location, right, we're going to access it. Now let's have an example of this. Okay, so now assume you have restarted your computer and this is the initial state of your cache. Okay, so you see all the valid bits are set to none or 0. They're not valid. Okay, we have 8 blocks, and each of the words are 1 word block. So this is the size, and the architecture is a direct map. Okay, So let's see how we're going to determine if this is a miss or a hit. All right. Now let's see. The first reference comes. It is 10110, right, in base 2. If we convert it to 10, that would be 22. Okay, so that's the first reference. We were trying to execute a code, and then we have to reference this code. This address needs to be referenced. Okay, now this comes again based on the architecture of a direct map memory, and we have 8 blocks. So the last 3, which are representative of my block number, should be first checked. Okay, the last 3 bits represents what? 110. Okay, or the block number 7, right? 0, 1, 2, 3, 4, 5, 6, 7, right? So it shows that I need to look into this block and see if I can find the tag 10 there. As you know, it was the initial state, nothing was there already, and the validity, the valid bit were none. So of course we're gonna have a miss. That's why you see a miss here. Hit or miss, we missed it, right? So we were looking for a tag of 10 based on the reference. It wasn't found. Now we went to a lower memory, which is the memory. So here was the cache, right? We went down to the memory and brought back the reference of mem of 10110, which was the reference. Okay, so we had a miss, and we paid a penalty to come back down, find it in the memory, bring it back up, put it here into the data. Okay, now if out of a sudden my next reference that comes here right after that is going to be the same thing, I have my validity set, which is fine. I'm looking at the block 110, which is the 7th block out of my 8. Okay, I have something in there. Let's see if the tag matches, and I'm going to see that the tag, which is 10, is match again, so I don't have to come back again and bring it up because the data was already there. So that would be a hit for me. Okay, but since this is the first time I'm looking at this block, I had a miss. Okay, let's carry on, shall we? So the next reference comes. Now let's have a look at this reference address. So it's 11010, which is 26 in base 10. Okay. So that means that I have to take a look at the block 010. All right. Where is 010? It's the 3rd one. I have to look into this block. Okay. I have to look into this block if it has the tag 11. Right. This block was already not valid because it was in an initial state. So again, the same scenario happened. I went down to the memory and found the result of this and brought it back up as the data. So the data would be the memory address of 11010, okay, that I was hoping to get, which I couldn't get. That's why I had a miss. All right. So I carry on the execution of the application. Another address comes here, which is 1011. Okay, now I'm gonna look at the block size 110. I'm seeing that the same tag is gonna get reused again. So, and I'm gonna look and I see if this one is there. It was already there. That's why I have a hit now. So there's no way, there's no need for me to just come down in the hierarchy of the memory and found it elsewhere, right? So I have it already there, so that would be the hit. Okay, so we are good. The next reference comes 11010. Again, this represents 010, which is this. The tag was 11. It was already there. Again, I have a hit. Okay, it shows that I'm accessing those items again and again. Perhaps I was in a loop. Either of them, either it was a spatial or a temporal one, right? It was getting used again. So on both of the references, I hit. So I could use the my cache, my memory hierarchy in my advantage. Okay. So both tags and index have to match. That's right. Yeah. Yeah. Index should be matched to find the block, and tag would determine what specific data it is. Okay. Because overall, these two will define the overall address. And if overall both of them were matching, so that shows that the memory of that overall is referring to the same data that we were looking for. Okay. All right, let's carry on. So now this comes 10000. So 000 shows the first block. Okay. I was hoping to find a tag 10. Nothing was there. The validity was null. It was not valid. So I set the validity bit to Y, which is a valid now. And then I paid a price. I missed, went down, and then found the data from the memory, brought it up. Okay. The same thing goes for this, which is the address 3 with the block of 011, which was this. The same thing happens. I was hoping to find the 00, wasn't there, and I went to the memory and fetch it, bring it back up. Okay. Again, we were trying to access this one, which we missed 2 references ago. Okay. Now we went here, the same block, the same tag, and it's already there. The valid bit is also set, so all good. Now we hit it. Okay, after one miss, we were trying to access the same thing. Now we hit. Okay, you see that the direct map is as a pretty intuitive and pretty straightforward method to access data. Okay, and it has its own pros and cons that which we will see later on in this chapter. All right. Then finally we have another one, and then we missed it again. Any question about this example before we go on a break? All good? Please write something on the chat so I understand. Okay, so let's go back and carry on at 7:30, okay, in 10 minutes. Okay. I've already talked about the format of the exam. We haven't concluded with the format. We haven't fixed it yet, but the way you're gonna be asked questions will be likely similar to what you've been doing in your midterm, right? Next week I'll be concluding with the materials of the course, and then the second on a second hour we're gonna review the final exam. I'm gonna walk you through the chapter 4 and 5, and then we either go with multiple choice questions, or we're gonna go with the same written text that you have to just write down and then send it back. So the only thing that has changed is the method you're delivering your exam, which is online, right? Instead of being physically attending an exam session. I'm trying to avoid having a multiple choice questions because they are very risky, and they, at some point they're not very well representative of your ability to have your exam. But if we didn't found a better way, you might just go with the multiple choice question. But for now I'm trying to avoid it. Nevertheless, the exam questions are not something new, right? You had the same experience with your midterm, right? One session before I reviewed the materials of the first 3 chapters, and then you had your midterm very close to those. The same thing applies to your final. You will have some examples on chapter 4 and 5, and also next week I'm going to review it in the slides, so you have enough of sample questions to have. What do you mean by that? Cumulative. Since we've already been tested with the first 3 chapters, I don't think it would be cumulative. And since you polled to decrease the weight as well, so we might not be able to cover it for all the chapters. So you're going to be asked mostly about chapter 4 and 5. Nevertheless, you've already been thought about the first 3 chapters, right? Some of the knowledge in chapter 4 requires understanding of the first 3 chapters, but you're not directly getting asked anything from the first 3 chapters, right? Yeah, thankfully we were able to adapt to the new environment after switching online, because the majority, your midterm was already done, the majority of the labs were done, so we are almost done with the lab, so there's only one left. And you also pulled to decrease the weight for the final, so nothing really changed for us. We were lucky on that domain. So can you see my video on the slide screen? Oh, I'll put it here. Now you can see it, right?
Professor?
Yep.
After the classes, how do we get the recorded video on the Moodle? Like, where you post it?
The course? Still
Yeah,
no?
No, yeah, the video record this
So
course.
I've done it throughout the course. I put it in that playlist of YouTube. You didn't see it?
Oh, I didn't see it.
Oh, so last week also I put it in the playlist. Let me give it to you. So you need to always check my announcements. I normally put everything in the announcements.
Okay.
But here is the playlist. So this is the playlist of the last semester. If you go on that playlist, number 24 was your last week lecture. Tonight I'm gonna add 25th to that, and which is gonna be tonight's lecture. Can you see my video now, or still not? Because I put it on the other pane. Should be on top of the slides.
Okay.
Still no? Strange.
Yeah. Okay.
Strange. Now the window you see is written part 2, right? I'm just trying to make sure if you're seeing actually the slides or not. Okay. On my laptop, I can see my video on top of the slide too. I'm not sure why you don't see it. I see. The rest is, yeah, the rest is blank in this slide, yeah. Let me see. Now you should see the address subdivision, right?
Yeah, Professor, I think you need to change the share screen. So when you click share screen, you click what you want to show.
So
Okay.
now the slide you see is address subdivision, right?
Yeah.
So this is the correct one. I'm just trying to understand why you don't see my video on top of it. Because I'm
your
recording
video.
my video as well.
Oh no, we can see your video.
Oh, we can see my video? Okay.
Yeah.
Oh, because people said no.
I think we thought we see another video. Like a video.
Oh, I see. I see. Okay. All right. So all good. Okay. So let's get started. We already talked about. Just put it here. This one. So we already talked about the direct map cache, and you understood how easy it is to fetch data when you're referencing, when you're trying to reference a memory address. First, you look at the blocks or the index, and then you check the tag, and then if it was found with the valid bit of 1 or yes, it's there, it's a hit. Otherwise, you're gonna go to memory and find the address with the memory address, and then you bring it back up. You pay a penalty, we call it a miss, and then you found it. Okay, so now let's zoom in to see how we actually do that, right? So here it shows there is a relation between the address of an architecture of a computer, right, and the cache and the memory. Okay, you can't just randomly put these numbers together. All right. So that was your valid bit, that was your tag, and that was your data. Okay. So if you have 64 bit for your address, if you have 64 bit for your address, okay, and you're using a direct map, normally the lower portion of the address is used to select a cache entry consisting of a data word and a tag. Okay, we call it sometimes offset, a byte offset. All right. With the block offset, we are actually supplying more information for a large RAM data. So in this example, we have 64-bit address. We are using 2 bits for byte offset, so 0 and 1. And from the bits 2 up to 12, we are actually using those bits for the index, right? And for the rest, we are actually using the tag, okay? And you see here how we're gonna determine what index, right? And then check the valid bit with this. If it was valid and the tag was found, we're gonna find the data, all right? Otherwise, we have to find it in the memory hierarchy from the L2 or perhaps memory. All right. So for instance, depending on this specific example, we have the indices. We have the indexes from 0 up to 1023, right? Why? Can anyone mention why we have this 1024 indexes?
Because when we have 64 bits, isn't it 1024?
64. Because we have 10 bits here.
Yeah.
You have 10 bits index, right? So this can represent 2 to the raise of 10, which is 1024, right? So
Yeah.
the number of allocated index bits can represent all my indexes, right? Or indices. And that's why we have this. Now, out of those 64, we allocated 2 for the offset and 10 for this. And that's why you have only 52 left for the tags, okay? So you can go from this way as well to compute the tag. Even if the tag wasn't known, you understand we have, if you have only 2 byte offset, 0 and 1, and then 10 bit for the index. So the resulting would be 64 minus 2 minus 10, which will be 52, okay? So that's pretty much a simple architecture of a direct map, okay? Let me see the chat. Right, yeah, that's right. Okay, so another example. So we are trying to address larger block size, okay? Now we have a 64 blocks, okay? And the way we address it is 16 bytes per block. Each of those blocks, right, in cache contain 16 bytes. Okay, that's why we call it 16 bytes per block. To what block number does address 1200 map? Okay, you simply understand what actually address 1200 is. Okay, since each of those addresses are 16 bytes block, so you have to divide this 1200 to 16 to understand exactly what block address is it, right? Which is 75. So that would determine what block number this 1200 maps to, okay? All right, so that's the block 75 because each of the blocks were 16. So 75 multiplied 16 would be 1200. Now, the same goes with the classic way we found it. We just do a mod 75 mod 64 because we are now having 64 blocks, right? On that example, we had 8 blocks. So we were modding into 8, like 0, 9, we're mapping to the first one. Now the blocks are larger, it's a larger cache. So instead of 8, we have 64 blocks. So the resulting block should be mod to 64, right? And the remainder is 11, right? 75 mod 64 is 11. And then you understand that address 1200 will be mapped to block 11, all right? Is that clear? Shall we continue? Right, yes and no. Okay. So, by by expanding this from that 8 blocks of the first example to this 64 blocks, now we're going to see we might be able to have address reduce or address miss rates, right? By reducing miss rates with larger block size. So the larger the block gets, you might have a reduced miss rate, okay? Because we are addressing actually spatial locality. If we are playing around with a large array of data, like our A of I, okay, is, I don't know, from 0 to 1024, okay, that means that you have a large array of data from 0 to 1023, right? The larger the number of blocks in my cache is, I might be able to address a spatial locality, because I might be able to put the larger chunk, the largest chunk of this array inside my cache, and I know that in my for loop, for instance, I'm gonna use them one by one, or the ones next to each other, right? And that was resembling a spatial locality, because my application in a for loop is accessing A of I plus 1 or A of I minus 1, and then use them at the same time to just multiply to each other, right? There are so many scientific applications that in order to calculate perhaps A of I, you need to access A of I plus 1 and then perhaps divide it by A of I minus 1, right? There are so many applications in science that does this, in scientific computing. So by having a larger block, you might be able to address this spatial locality, right, and reduce the miss rates. But if in a fixed size cache, right, the larger the blocks goes, because you have a fixed amount of size, right, you're gonna have fewer of them, right? If you have a size of 64, if each of those are 32, you might have 2 blocks, right, because the size each of them are 32, right? So the larger the blocks goes, now we're gonna have a more competition to put those blocks inside each. Now, at the same time, now we are increasing the miss rate, so we are going against the purpose, right? So that's why the larger the blocks get in a fixed size cache, which is pretty much all the time, you're gonna have more polluted data and more miss rate, okay? All right. Now, cache misses. As I implicitly mentioned throughout the lecture tonight, on cache hits, everything is normal, right? We were trying to reference a memory address and we found it in the cache. It hit and we just have the data right away, right? Everything proceeds as normal. But on the case of a miss, what is happening in the data path actually is we need to stall the CPU pipeline, because remember, cache, your first level cache, which is the highest speed, matches your pipeline, okay? So the CPU pipeline from instruction fetch, ID, execution, mem, and write back, right? They were working normally. On the first miss, now everything should be unstalled, because now the speed you're gonna fetch this data that is missing is gonna be slower than the speed of the pipeline. Now you have to stall the pipeline to find it from L2 or from memory, okay? Now you have to stall the CPU pipeline, and then we need to fetch the block from next level of hierarchy. So if it was L1, we're gonna go to L2, or if it had only one L1, we're gonna go to memory, right? Now, because of this, we're gonna have instruction cache miss. And we have to restart the instruction fetch, right? And we're gonna find the data which was missed, okay? So in a nutshell, we can say that a request for data cannot be fulfilled because it wasn't found, it wasn't present in the cache. So I need to send my PC value to the memory, right? It would require more time. I have to install it now. And I have to restart the instruction execution again at first step. And that's exactly the the reason why we have a penalty term involved when we miss. Okay. So there's a term called write-through, and it's a scheme in which it writes always updates both the cache and the next lower level of memory hierarchy at the same time. Okay, ensuring that when we do that, we're gonna ensure that the data is always consistent between two, right? No matter what, if it hit or not, we're gonna just go back down and then update both cache and the memory at the same time. For instance, if you are trying to execute a loop and you are accessing AI plus 2 and it was found in your L1 cache, right? As you update your AI plus 1 in your cache, you're going to update the memory location of AI plus 1 in your memory as well, because now you have a new updated assignment for your AI plus 1, right? And your cache has the most recent one, but your memory doesn't. So this write-through scheme ensures that both of them are getting updated at the same time. Okay, I mean, of course, your memory would be updated later because it's slower, but that's why you need a buffer here. You need a write-through buffer, and then it's gonna propagate this in your memory as well. All right. So, for instance, I mean, you can easily understand why it makes write takes longer, because you need to update them both at the same time, right? So if the base CPI is actually 1, so 10% of our 100% of instructions are stored, right? And write to memory requires 100 cycles. So the effective CPI, which turns out as a result of a write through, which updates both the cache and the lower level of the memory, is going to be that 1, the old one, plus 10% of the time that we are updating, which requires 100 cycles. Okay, and it would increase our CPI dramatically, right? Now our CPI from 1 turns to 11, which is very, very bad. So the solution was to have a write buffer. Okay, so so this is your cache, and that's your memory, right? So you update this block in cache, and then the buffer, the write buffer here, makes sure that after some time, right, or after some wait, this result that was updated in cache will be updated in memory as well. However, this buffer ensures that your pipeline goes as smooth as possible, right? Your CPU continues immediately. Your pipeline goes as follows. There's no stalling in it, right? So that's the reason we might need a write buffer for the write-through scheme. Alternatively, we can have a write-back, right, which is a scheme that handles writes by uploading values only to the block of only to the block in the cache, right, instead of write-through. Then writing the modified block in the lower level of the hierarchy when the block was replaced. So these are two different schemes that normally are used in cache. You don't have to memorize it again, but just for your information, we have write through and write back. Okay. Now let's have an example here. Okay. In intrinsically fast math is an architecture. It's the name of the architecture, right? Okay. So it's been very well known for embedded domain, for like cell phone devices or embedded devices. It had worked on MIPS processor instead of RISC-V. It had MIPS, so another type of instruction architecture in ISA. And instead of 5 pipeline, it had 12 stage pipeline. So your pipeline, which is 5, which is instruction fetch, instruction ID, execution, memory stage, and write back, right? It was 5. In that architecture, it was 12 stage pipeline. All right. So the instructions were split into instruction I cache, all right, and D cache. So many of the architectures are splitting between the data cache and the instruction cache. Okay. D cache contains the data, and I cache contains the instructions. All right. So that was the architecture of this intrinsically fast map. Each had 16 kilobytes, each of those, and within this size of 16 kilobytes, you had 256 blocks of 16 word blocks. If you multiply them, that would be each of those 16 kilobytes, okay? And your D cache or your data cache was using a write through or write back, all right? So this is the experimental results on the benchmark of SPEC 2000, right? Remember in chapter 1, I was talking about some of the benchmarks. So SPEC 2000 contains a number of applications that they have run this architecture with, and by running them, they understood on average, they had 0.4% I cache miss rate and 11% data cache miss rate. And the weighted average of these two was 3.2%, okay? That's just for your example. You don't have to memorize the architecture of intrinsically fast map, but it's just gonna give you some idea of how they implemented their architecture. Instead of 64, it had 32, right? And in order to optimize the way they were accessing in their cache, they were using some multiplexers, okay? So that the tag field is 18-bit wide, and the index field is 8-bit. So now that would give you a 4-bit field, which is the bits from 2 to 5, right? Is used for index for the block, right? And now we have to select the word from the block using a 16-to-1 multiplexer, okay? That's why we need all these multiplexer to select the data. So that was one way to approach this. Again, you don't have to memorize this, that's just for your example. All right, so let's have a more practical example. Now, assume here, okay, we are using a main memory with a cache, okay? Let's see what happened here. No, you don't have to memorize it, no. Never memorize anything in computer engineering. Try to learn it. Okay, so we are using a DRAM for main memory, okay? Our RAM is the classic RAM, which is DRAM. For instance, we are not using a hard drive or a USB key, right? And our size for the block of memory is by word, okay? Each word, again, I'm just running into issue with the digital pen now, okay? And using a question statement, you might find what's the size of the word later. And we have cache supporting this memory, okay? So we're gonna have one bus cycle for address transfer, 15 bus cycle. So one cycle it takes to transfer the address, 15 cycle it takes to access DRAM, and one cycle it takes to transfer the data we access it, okay? So we have a 15 cycle and one cycle, okay? So if you just simply compute it for a 4-word block, right? If each block contains 4 words, and our RAM was 1-word wide RAM, right? So the miss penalty would be what? 1 plus 4 by 15, 4-word block multiply by 15 because of its accesses, and then 4 multiply 1 because of the transfer, right? This is for the address transfer, this is for access, and this is for data transfer, right?
Why don't we multiply the first one by 4?
Why 4?
Yeah, the miss penalty is equal to 1 plus 4 times
But
15.
address transfer is always 1 for each of the
Oh, okay, okay.
Yeah, right. Okay. So that's why you add them up. It's going to be 65 cycles, okay, for the miss penalty. And it's going to lower our bandwidth from 16 byte divided by 65 cycles, which is going to be a very, very slow number of 0.25 bytes per cycle, right? So at each cycle, the bandwidth we're going to use is going to be 0.25, okay? Okay, now let's add some more stuff as cache onto this memory, okay? Now, we have a, remember, we had component of CPU time, right? Now we have execution cycles that are included with the cache hit time, right? Because if we hit with cache, everything goes as normal, right? Which is showing that your program executes. Then we're gonna have some memory stall cycles, right? Which we will use mostly for cache misses. We weren't able to hit, so we have to stall, and it is dependent on the number of times we miss, okay? If we simplify it, the memory stall cycle would be what? The memory accesses per program, so that was a normal case, which is the hit case, multiply those irregularity, right? Those times that we miss. How are we going to compute that? We're going to have a miss penalty multiply the rate in which we are missing, okay? And that would be the overall scheme of number of stalls we're going to have, okay? Memory accesses per program. Out of those memory accesses, we might miss some of them at some rate, which is 10%, 15%, or whatever X percent. For each of those, we are paying a price of a miss penalty because we have to come back down, stall, come back down, and then find it in memory and then bring it back up, okay? So that's why you have to multiply these three values, which are, again, equal to instructions per program, multiply misses per instruction, multiply miss penalty, all right? So this is the way we can measure the performance of cache while we are running some executions, okay? Executions of some instructions, all right? As an example, let's have a look at this one. So we have an instruction cache miss rate of 2%, okay? Our I cache misses 2% of the time. So on 98% of the time it hits. Our D cache, which is for data, right? Normally we just take an average of these two. Miss rates 4%, all right? So on the cases that these miss, we have to pay a penalty, right? The miss penalty involved because we need to come to memory and then fetch the reference the memory, the reference to the addresses from memory. It's going to take us 100 cycles, all right? And our ideal cache, or an ideal world, which is considering everything was going flawlessly as normal, it would take the CPI of 2, right? Which we call it the base CPI. So without any misses, like with 0%, if these two were 0%, that would be a 2 CPI, all right? And we know that 36% of our overall instructions are from load and stores, right? Those that will use this to miss, okay? Now, we're gonna determine, the question is determine how much faster a processor would run with a perfect cache that never missed, okay? So now we need to first compute the miss cycles per instructions because we have so many instructions. We need to find the miss cycles per instructions, right? We knew that iCache was 2% and we had, right? So that would be 2. our D cache was missing 4% of those instructions that are only dependent on the load and store, right? Because load and stores are involving with data, okay? Is that clear? So that would be 1.44. And you add these two up, that's going to be a total of 3.44 per instructions, right? Remember, 36% of our instructions were load and store, which involve a D cache. And then 4% of those time, okay, we were missing. So 2% of the 100 were like 2. 4% of the 36% of the load and store would be 1.44. You add them up together, these are average numbers, so it's going to be 3.44. We're going to have missed cycles per instructions on average, okay? Now, by just adding this, so the CPU time with stalls, which the case that we have, and a perfect CPU time with the perfect cache that never misses, all right? So we have to determine what would be the ratio between these two, okay? This would be so in number of instructions multiply their CPI, multiply their clock cycle. This one would be the CPI of the perfect case, multiply clock cycle, all right? Now we have determined the I's for this. So by just dividing these two, you can easily see that it's going to be 544 divided by 2, which we were given to us as a base. And the actual CPI would be 2 plus 2 plus 144, which is 544, okay? We can also say that this is 2.72 times faster, the ideal CPU without any misses. Is that clear? I'm just gonna stop here for a second so you have a chance to look at it. So this is how we computed that 544 there. And that was the base that was given to us, right? Base, the CPI. So basically, what you have is a base CPI plus the D cache missed cycles plus the I cache missed cycles, right? That's the overall new with the stalled CPU. Is it clear? Shall we continue? Okay. So there is another formula to compute the performance, which is take into account the average access time or average memory access time, right? It is known in computer architecture as AMAT, or average memory access time, right? We're gonna take into account the hit time, those times that everything goes as normal without any misses, right? Because the average memory access time consists of those times that you had hit the cache plus the rest of the times which you missed. And in order to compute that, you have to just have the miss rate plus the miss penalty, right? But assume you have multiple levels of cache, this gets multiplied by the L1 and the miss penalty of L1 and L2, and then miss penalty of L2 and L3. So you just gets longer and longer, but the notion would still remain the same, right? You're gonna have a hit time for those cases that hit. For the rest of the cases, you're gonna have a miss time. And the miss time will be computed as a miss rate multiplying miss penalty, right? You can call this as miss time. So if in a question it was given to you as miss time, miss time is always equal to miss rate multiply miss penalty, right? All right, so let's have an example on this. So we have a CPU with 1 nanosecond clock, right? The hit time for the CPU takes only 1 cycle, and the miss penalty takes 20 cycles. You see, if you hit, everything goes as follows, normal, 1 cycle. If you miss one, the miss penalty you are given is 20 cycles, right? And your iCache miss rate is 5%. So 5% of the time, your iCache misses. On 95%, you hit, all right? Let's compute average memory access time. So easily you can compute your hit time is 1, and 5% of the time, in a miss rate of 5%, you're gonna pay the price of 20 cycles, right? So although your hit time for the 95% was 1, because of only those 5%, which gives you 20 clock cycle penalty, your overall, your average memory access time went up by 1 cycle, right? So you doubled the amount of execution by only missing 5%. Okay, does that make sense? All right, let's carry on. So the performance summary, if you want to summarize what we've been discussing so far, is when CPU performance increased, right, miss penalty becomes more significant, because the faster your CPU goes, you want to make sure you don't miss, because if you miss, you're going to pay a huge price of your very fast CPU and very high number of miss penalty and perhaps way slower memory, right? So you want to make sure you are having as least as possible or decrease as much as possible your miss rate. All right. So far, we've been talking about the direct map cache, which was one of the 3 different architectures of cache. Let's talk about the other 2, which are pretty easy as well. So the other 2 are in a category of associative caches, okay? So the category number 2 is called fully associative, right? And number 3 is called n-way set associative. And the first one, if you recall, it was direct map. Okay. So direct map is one side of the extreme spectrum for which you can have only one choice for your data to be placed in a block, and you just figure it out by a mod, right? You get a mod, and then you understand the block, and using the tag, you want to understand, okay, if it's a hit or miss, right? If you want to just go very large, you might have some offset as well. On the other extreme side of the spectrum, we're going to have a fully associative cache, right? Which is number 2, for which it allows a given block to go anywhere in a cache, right? Exactly on the opposite side of the direct map. So these 2 are actually opposite. Direct map is exactly opposite of fully associative, right? 2 sides of the spectrum. So on fully associative, it's going to allow a given block to go anywhere in a cache entry. And so at the same time, this might be, okay, that's not bad. But the point is how you're going to search all of the cache size. Although this is smaller than memory, but it's going to require some time to implement some hardware techniques to search throughout the fully associative cache, right? That's why we have a requirement here so that all the entries to be searched at once, right? In order to do that, we need to spend hardware. So it's going to get more expensive. So we need to have something to compare the values per entry for all of those blocks, right? That's why we need to have comparators per entry, which in hardware is always expensive, right? So you have one side a direct map, on the other spectrum, right? You have fully associative. Somewhere in the middle, so that's this side, and this is this side. So somewhere in the middle of this spectrum, you have n-way set associative. So n-way sits here. Now, instead of fully associative, we have n-way set associative. Instead of a random allowance on every entry, you're gonna have only n entries to search for now, okay? It's not a fully associative, it's n-way set associative. And that's why the name resembles the same, because instead of a full, it's n-way set, right? Depending on the n, you have different number of entrants, okay? So each set contains n entries now, and we need to find a way to find that, and the easiest way is going to be again another mod, right? Block number determines which set now. Which set? Each block has some set inside. Okay, so in order to find that, we just have to have a block number modulo number of set in the cache. So n-way set, if it was 8, this would be 8. If it was 4, it's going to be 4. And that's why we have different names for n-way set associative. You might have 2-way set associative, 4-way set associative, 8-way set associative. Okay, that number determines the different entries. Okay, and then inside each of those entries, inside each of those ends, you have to treat it as a fully associative. Now inside that, it could be anywhere. All right, so that's somewhere between your direct map and fully associative, having n-way set in the middle. Okay, now instead of comparators for all of those, right, now we need to have comparators for some of them, right, which is less expensive. Each of them has pros and cons now. All right, now we're going to see what's the difference between these two. Okay, any questions? Okay, this is an example of all three together. Okay, direct map, you have 8 blocks. Okay, each block can only represent one set of indexes, right? You have 8 blocks, so you understand that, okay, I have to search only this block in order to find it, and I have to just check the tags, right? The tag could be either, I mean, in this case, I have 8 places to search for, right? My optimization space is only 8, so I have 1/8, and I know exactly where to go because I know, because of the mod that I have to just only search this one, and inside this, which I already know I have to look for, I just have to check for the tag number, right? Either this tag or that tag. Am I going to hit or am I going to miss, right? If the valid bit was set, I understand soon if I miss it or I hit, okay? On the other side, this could be anywhere, right? So my search space expands from 1 to all of them. Now these should be the comparators I need to search for, right? At the same time, because this cache allows us for having a fully associative cache, all right? So the for the block address of 12, right, this can appear in any of those, right? Assume you're addressing 12 here. So somewhere in the middle, we have n-way set associative. Now the set number is 4, right? I have set 0, set 1, set 2, and set 3. We can easily understand I need 2 bits here, right? I need 2 bits here. I need 2 bits here in order to determine which set I'm looking for. Okay. So, and this determines the architecture of my cache, which is n-way set associative. Okay, now if I have to search for this, I only have to search for set 0, okay, which is either this or the other one, right? So that's why my search decreased a lot from all those 8s to only 2, because I'm discarding the remaining sets now, all right? Inside the set 0, I have 2 options now to search for, okay? Does that make sense? Any questions? Write a feedback for me. Okay, so your friend is asking us how we gonna understand why which set are we looking for. Okay, the tag was 12, right? Remember we had to get a mod. We have 4 sets because it's 4-way set associative. So 12 mod 4 is gonna be what? I'm sorry, 12 mod. Actually, it's just 0, right? 12 mod 4 is going to be 0, and we have to look for set 0, right? We have 4 sets. Which of those sets 12 is going to be looked for? 12 mod 4 is going to be 0, right? The set 0. Does that make sense? So now we have only this to search for. For the fully associative, we have no idea which of them to look for. So that's why we need to have comparators to search for all of them. All right. For the direct map, again, so that was 12, but in order to understand the block size, we are looking for the block, okay? That's why it's going to be modulo 8, because we have 8 block, and that would give us number 4, all right? That was number 4 here. Is it clear? Okay. All right. Now, whatever questions might come from this chapter, it would be just to play around with these numbers, right? If you understand what's the difference between a direct map, an n-way set associative, and fully associative, it would be just easy because you're just playing around with the block size and index, and that's all. All right. That wouldn't be any more difficult than that. So for finding a position of a memory block on a direct map, we're gonna have a block number mod number of blocks in cache, just like what we had in the previous slide. So it was 12 mod 8, right? On a set associative, what we need to mod is not a block anymore; it's a set, because inside a set it could be gone anywhere, right? All kinds of elements of the set must be searched inside a set. If it was in set 0, depending on how many blocks it had, how many tags it had, it's going to be searched. On a fully associative, the block can go anywhere, right? All tags of all blocks must be searched now. These 3 different things. Now, let's have an overview of all these 3. How are we going to go from one side to the other side, right? Okay. Let's just start from this. And you can easily understand that a direct map, right, can be also called a one-way set associative, because this was representing the blocks, right? So one-way set associative is actually a direct map for which we have only block number, which is a mod of the actual number, right? And for each of those blocks, we have a tag and data. As simple as that, right? For the two-way set associative, now we distribute the chunk of the cache size, and remember, all of these are having the same size. The way the architecture determines how we're going to place the data on is different, right? But overall, the data size, the size of the cache would still remain the same, right? So we have two-way set associative. So now we have two-way set. So we have sets with 2 bits, which is 4 sets. And each of those sets contains a tag data, tag data. That's why we have two-way sets, one-way, two-way, okay? Set 1 has two-way sets. For each of the sets, we have two-way to place data on, right? We can increase this. We can have 4-way set associative. So for each of those sets, we have 4 ways now, 4-way set associative. Now we have to look for 4 places at the same time. We need 4 comparators, right? And then based on this, because we had only 8, right? We can go up to the extreme side of 8-way set associative. And this will effectively removes all the blocks. And this is going to be a complete or a fully associative cache, right? Now I have to search everywhere, okay? I have only 1 set. So you can see by playing with the set from 1 up to this, you can come from fully associative to direct map, all right? Any questions? Direct map is, I mean, there's no notion of one set is fully associative, right? Because here, if you look at it, this is 1 set only. This is set. In direct map, we have ways per set, is one way per set, okay? For each of the, and that's why we have blocks there. Yeah. Is it clear? All right. Let's have one quick example, and then we're gonna conclude the lecture. And then next week we're gonna talk about a few more examples, and then review the final exam. All right. So now we have an example about associativity for cache. So we are comparing 4 blocks cache. So if you go with direct map, or a two-way set associative, or a fully associative, right? And the block sequences are coming from this 0, 8, 0, 6, 0, 8, 0, 6, and 8. Okay. If we go for the direct map, right? For a direct map, what's going to happen is you're going to just go down with the entries, right? 0, 8, 0, 6, 8. Okay, these are coming here. So for 0, the cache index would be 0. Nothing was there already. You're going to have a miss, all right? That's for 8. For 8, you break it down, because here you understand that 0 mod 4, right? We are 4 block cache. 0 mod 4 is 0, right? So we're going to go on the cache index of 0. For 8 mod 4, we're going to go to what? Oh, I'm sorry. For 8, yeah, it's going to be 0 again. And then we have 6 mod 4. This is supposed to be 6 mod 4. 6 mod 4 is 2. right? So we have 08068. So for 0, it's going to be index 0. For 8, it's going to be index 0 again, cache index. For 0 again, it would be 0. For 6, it would be 2. That's why we have 2 here. And then the other 0 is going to be 0. All right? And in all of the cases, nothing was there before, right? So we missed all of them because here was empty. And in all of the cases, we had to just go down to memory. So memory of the 0. We look for this address and reference the address and bring it up from the memory. For this one was memory 8, memory 0, memory 0, and memory 8. Okay? Does that make sense?
Can you just explain again the memories?
So these memories are showing that you missed because nothing was there. So those things that used to be there were these with the black color, right? The other things that you updated are coming from the red, all right? Nothing was there here, so on all 5 cases you missed. This one was memory of 0 was here, but because you were addressing the cache index number 2, you had to just go back again and bring it up. So on all cases you missed.
Why do we have 2 on the 8 block address?
This one?
Yeah, so
because 6 mod 4 is 2, right? So the index we are accessing was here actually, and nothing was there already, right? We were accessing in the index of 2. So again, we missed, and we go back to memory, and then the memory of 6. The result represents the data, right? Because it returns mem of the address. Mem of an address is actually the data, right?
Yeah.
You pass it an address, and it's gonna output a data, but this requires some cycles with a penalty, right? So these are actually will be data that are coming from memory. Okay.
And on the last line, is the memory 6 inherited from the previous line?
Yes. Just have to read it from. So it was gradually completed line by line.
So if we had another line below 8, it would also have mem6 on 2?
If we had another line of 6 and 2, it would be hit, right?
No, I mean, if we had another line below 8, would mem6 be also inherited or passed down to the...
Yes. Because as long as you set, which is, I assume, you set the valid bit to Y, it's going to go on, right? And gradually it might just be completed. And then you have to override at some point.
Yeah.
Does that make sense for everyone? So we've got question: if you hit 8 twice, why are there 2 misses? Since if you oh, I see. Yeah, actually you're right. Yeah, this is a typo here. This should be hit. Yes, this should be hit. I'll fix this. Yeah. This is the slide of the reference book. Perhaps they've made a mistake. Yeah.
Would anything else change on the table other than the miss for the correction?
No.
Okay.
Okay. So normally for the tag, the remainder of your address would be the tag, depending on the size of the block. For instance, if you had 32 in memory, and you had 8 blocks in cache, right? So for 32, you need 5 bits to represent that, right? And for 8 blocks, you need 3 bits because it's gonna represent 3 bits. And the remainder was the tag for you. You can always, Eric, you can always compare it this way. We're gonna have examples on this, and you're gonna completely understand how you're gonna do that. From the overall size, you can just remove the block size, and then the remainder would be the tags. Yeah, I guess so. Yeah. This could have been shown better. Yeah. Actually, misses are shown here because actually looking at this, you're gonna understand. Yeah. Okay. All right. So now, having the same question, what if we had a two-way set associative or a fully associative, right? So we had again 08068, 08068. So for the two-way set associative, now what you need to compute is the set as well, right? You have 2 sets now. So for 0, for all the zeros, 0 modulo 2 is going to be 0. 6 modulo 2 is going to be 0. And also 8, you have 8 modulo 2, 0, right? That's why all of those will be placed in either of the sets, okay? So, because we have a choice of which entry now we go to, right? We need a replacement rule now, right? So sometimes when you have to override your cache, you need to have a replacement rule. Sometimes you use a list recently used, LRU, right? Or a most recently used. Sometimes you need to override the data on top of each other, okay? For instance, in this case, we are using a least recently used method, right? Which is the block that was used furthest, right, in the past is going to be replaced, all right? So for instance, when block 6 is referenced, okay, you understood that 6 mod 2 is going to be 0, so it's still going to be set 0. Since block 8, right, among the two has been used the furthest in the past because it was older than the 0 one, right? So we're going to replace it with that, okay? Does that make sense? So in caches and mostly in n-way set associative, sometimes we find a way, sometimes we have to override data, right, in a set, okay? So because normally many of the cases we might access the same set and it's random inside, right? So we have to find a policy to update the data inside a set, okay? So for set associative caches, in this case, we are using a list recently used. So the one that was furthest in the past, right? Like some instructions ago, further in the past than the other were used. That shows that, okay, we might not need to keep it for now. We can update it with more recent instructions, right, that are coming to the cache. So we can update those that hasn't been used recently. So the least recently used policy is gonna update this one on top of 8. Okay. Because 8 was furthest in the past used, and we are having a policy of least recently used update, right? We're gonna update it on the one that was furthest in the past used, because that would make sense because it wasn't used as often, right? So we might need to update it. Okay, so now if you go for the fully associative now, we have all the options now, right? So it has 4 cache blocks, right, in a single set. Of course, any memory block can be used. Any memory block can be stored anywhere in those cache blocks, right? The fully associative cache has the best performance here. However, it is spending more comparators because we need to check at the same time if the data was found or not. Okay, so 0 was going there. The first was missed. So you found mem of 0, you put it there, and an 8 came, right? You keep the 0 as well. You didn't find 8. It was another miss. So you found 8 and placed it next to each other. And then you have another 0. Now you had 1 0 already. You had comparators to check. You found, oh, mem 0 was there. So green is hit, right? So those hits are shown in green. Those misses are shown in red, right? So again, another 6 comes. So those updates are actually updates with the miss, I believe, in this slide. Those updates with the miss are shown in red. Those misses itself are shown in light blue. For instance, in this case, and also in this case. Because another 6 comes, right? That's the first 6. There was no mem of 6 already, so that's a miss, right? Another 8 comes. We had already an 8 here. We use hardware to compare the entries of the cache of the cache at the same time, and we understand, okay, mem of 8 was here, so that's going to be a hit, right? These are miss, and these are updates and miss by the policy of least recently used. We updated over 8 because we had 2 options, right? We had a miss here. No 6 was found up to this point. Up to this point, no 6 is found, right? We need to fetch the memory of 6. Now, which of these 2 we can place mem of 6? We have an option of 0 or 8. Least recently used tell you 8 was older, so replace it on top of 8. Keep 0 because 0 is more recent, right? Again, for the 8 comes here, we have mem of 6, mem of 0. Which one to replace? Now comparing to 6 and 0, 8 is older. I'm sorry, 0 is older because 6 is just recent. We update it on top of 0. Okay, you got it? Yep, that's right. All right. Any other questions? So I'm just going to conclude tonight's lecture with this slide, which is there's a trade-off with how much associativity, right? So on average, if we increase associativity, we're going to decrease miss rates, right? However, we're going to use more hardware, right? And results has shown that, for instance, a simulation of a system with 64 kilobytes of D cache and 16 word block on a Spec 2000 benchmark, it shows that One-way set associative has 10% miss rate. This is a fully associative recall. Two-way and four-way are a little bit lower, and eight-way, which is, so this is a direct map, and this is the fully set, is minimally better, right? Slightly better than the four-way and two-way with 8.1. Normally in real world, normally they are somewhere around this, depending on the architecture. Normally they use caches from two-way, four-way, and eight-way. All right. Okay, guys. If there are no more questions, I'm gonna wrap up tonight. There are some slides left, mostly with examples of cache. We're gonna talk about it in the first hour of next week, and on the second hour, we're gonna conclude with other examples of cache and also chapter 4 for your final. All right. Make sure.
I have a question about the labs.
Go ahead.
Lab M and the last two labs, are you gonna, like, how are they gonna be graded? Like, is it gonna be?
I was actually telling your colleagues at the beginning of the course, at the beginning of tonight's lecture. So I asked your TAs to evaluate it as a whole. So they're gonna see all your all your answers. They're gonna check the similarity report that I mentioned with your colleagues. We wanna make sure all of you have spent time to write it yourself without any external help. And then by having only a single or a couple of mistakes, you're not going to lose marks, but you're going to be evaluated on the overall performance of all the problems, because some of them are going to get stacked up onto each other, right? If you miss one issue, the rest would have a sort of a cascade, effect. So I ask your TAs to make it uniform so that everything is normalized, and then you're going to be evaluated as a whole. I don't think that there should be many major differences, right? Because you already had your 6 labs, and there are only 2 labs left, which is now only 1. And by this Friday, you're going to be done with that. And then next week, we're going to wrap up the course with some examples of cache and the review of the final. And then you're going to be ready for the final, okay? Meanwhile, I'm going to upload the examples for chapter 4 and chapter 5. And you're going to get to know more, sense of how we're going to test on your finals, okay?
But is it possible for you to upload the answer for at least lab M, like the last question? Because my output wasn't matching that at all.
You can ask individual questions about it, but if uploading the answers of the lab will effectively nullify all the efforts of me and my colleagues in order to make that lab. We have to start from scratch from next semester, right? Do you understand what I mean? Hello? I guess your colleague is disappointed. What happened? Somebody, is he here? I can see him. Somebody raised hand. If you want to speak, just speak.
I raised my hand, but
okay, yeah, go ahead.
That was during the lecture. It was a long.
Oh, I see. Oh, I guess okay, that's fine. Yeah, perhaps he got disconnected, right?
Yeah.
Update the heat maps for the last 8. Which update? Which of them? For this one? For this? Which one? Albert? The first table? Oh yeah, actually, yeah, you're right. So guys, yeah, good call from your colleague. So this is still a miss, right? Because you have been overriding on top of MEM8 already. So think about it up to this point. Yeah, I got confused myself. Thanks for pointing out. So when we are here, inside our cache, we have this only, right? We have mem6 in the block 2 and also mem0 in block 0, right? Now 8 comes again, right? And 8 must go to 0. So you need to look for 0. And then 0 has mem0. You had to have mem8 here, which you already override, which was overridden already, right? So now the only chance is like you have to get it back again from memory. So that's why there's another miss, right? So this is still correct. Thanks for pointing out. Is it clear for everyone? So these are the incoming sequences, right? One by one. You read it this way. Okay. All right. Other questions? If there are no more questions, I'm gonna wrap up the lecture now. All right. Okay, guys. Actual CPI 2, I cannot really understand that meaning of the first one is the ideal CPI of 2, right? So you, no matter what, without any misses, you had 2 as your base CPI, and then the other 2, and then the 144 where the I cache misses and D cache misses, right? You have to add on top of your perfect CPI. Is that clear? Okay. So direct map would only hit if you try to access the same memory 2 times in a row. Not 2 times in a row. In this example, 2 times in a row. No, not even 2 times in a row. Because your line, your block address, your sequence address of 8 was followed by a 0, and recall both of them, their mod would be 0. So this one had placed on top of this. That's why you have this red here. You have overridden this one. That's why it's red. Okay. Now, if you have another 8 after this, which is this, you have to access block 0 again. So there's no mem8 here, right? So you have to have a miss again. Yeah. If you didn't have 0 here, up to this point, this would have been a miss. This would have been a hit. Okay. Yes, if it was an 8 and 8, that would be a hit for sure. Yeah. Other questions? All right, guys. Have a good night. I'll upload the video of tonight's slide later tonight. Okay? Take care of yourself. Bye. Have a good night.